Hi and Assalamualaikum. So we have done our lab which is M3, study of PN junction, and the objective of this experiment is to study the various characteristics of PN junction, to determine the reverse saturation current I0 and material constant, and the last is to determine the temperature coefficient of the junction voltage and the energy band gap. So for procedure part 1, we refer to figure 2. The diode was connected to be tested to the terminals of the right side socket with the polarity as indicated. After that, the voltage and current readings we have recorded respectively. For part 2, with the connection as in part 1, the oven and sensor was inserted into the respective socket. The diode in the oven was placed and the forward current has been set to a low value to avoid heating. And then the display 1 was switched to temperature mode and the oven temperature was recorded. 3. The PN junction was connected to the terminal on the left side socket. Display 2 has been set to bias mode and the oscilloscope was connected to the CRO to measure the input and output voltage for the specified bias and frequency settings. All the reading is recorded. For the data part 1, reverse saturation current I0 and material constant N, we record the current and voltage. For part 2, temperature coefficient of junction voltage and energy gap, we record temperature and junction voltage. For data part 3, depletion zone capacitance and its variation with reverse bias voltage, we use two values of frequency which is 5 kHz and 20 kHz, and we take 5 reading for each value of frequency and we record input voltage and output voltage.
Hi, I am Shakira. For this lab report video, I will explain about analysis part. For part 1, we have to plot graph and determine the reverse saturation current I0 and the material constant. As shown in slide, I already plot graph ln I versus V. This slide show LSM table that I calculated to find M and C value with their acidity for this graph. From M and C value, we can find material constant and reverse saturation current with their acidity. For part 2, we also have to plot graph and determine the temperature coefficient of the junction, voltage and energy band gap. As shown in this slide, I already plot the graph V versus T. This slide show LSM table that I calculated to find M and C value with their acidity for this graph. From M and C value, we can find temperature coefficient and energy band gap. For part 3, we need to describe the dependence of the depletion zone capacitance on the reverse bias voltage. And our answer is we observe that reverse bias voltage is rising, capacitance smaller that leading to decrease the output voltage. This impact the output voltage that will be remain almost constant. The capacitance impact increasing the frequency. This indicated that there is a dependency of the capacitance on not only the voltage but also the frequency, which is noted to be something worthwhile to be considered when processing diode in circuit.
Now I will explain the derivation of equation 6 as shown here. We begin with equation 6, where voltage is expressed in terms of temperature derivation of voltage, a thermal constant term, and the band gap energy term divided by charge. Next, we use the diode forward current equation, where the saturation current I0 depends on temperature and I is the diode current. We substitute the expression for I0 into the diode equation to get the simplified exponential form. Now, substituting this expression into our current equation, we get an expression that relates to temperature and voltage. To simplify further, we take the natural logarithm of both sides. This gives us a linear relation between ln I and temperature terms including V. Since we are analyzing at constant I, we differentiate both sides with respect to temperature T. This gives us an equation where the derivative of voltage with respect to T appears. We then solve this derivation equation for V by rearranging terms carefully, isolating V on the one side. Finally, we simplify the equation and recover equation 6 in the desired form. This derivation shows how voltage varies with temperature and helps us to analyze diode temperature behavior.
Question 2 asks to explain the origin of the depletion capacitance. The origin of the depletion capacitance arises from the charge storage behavior of the depletion region in a reverse bias p-n junction. In a reverse bias p-n junction, a depletion region is formed from the diffusion of electrons and holes in n-type and p-type region to neutralize the both regions of the p-n junctions. These regions acts like the dielectric in a capacitor. Both sides of the junction where fixed position ions on the N side and negative ions on the P side remains, forming layers that are two oppositely charged. Then, when a small AC signal is applied, the depletion width W slightly changes depending on the applied voltage, which causes a small change in the amount of charge stored on either side of the junction. Hence, depletion capacitance is when the junction stores charge in response to voltage, and the ability to store charge originates from the movement of majority carriers in and out of the edges of the depletion region. In this experiment, the characteristics of a PN junction diode were studied under forward and reverse bias to understand its electrical behavior. From part 1, a graph of ln current versus voltage was plotted based on the ideal diode equation. I equals to I naught exponent QV over NKT minus 1. N is the ideality factor. So the gradient and intercept of the linear region were used to determine the reverse saturation current I naught and the material constant N. The obtained material constant was 1.45 plus minus 0.01. Germanium with N equals to 1 was used as the diode material. In part 2, data from varying temperatures T in Kelvin unit was used to determine the temperature coefficient of the junction voltage. The forward junction voltage decreased with increasing temperature. From the VT curve, the temperature coefficient was found to be negative 1.2 MV per Celsius, and the energy band gap EG is equivalent to QV0 was estimated to be 1.151 V by extrapolating to 0 Kelvin. The objectives of the experiment were successfully achieved. The results verified the exponential current voltage behavior of the PN junction and allowed extraction of key parameters such as ideality factor N, I naught, temperature coefficient, and energy band gap, reflecting both electrical and thermal properties of the junction. However, the results, especially in part 2, were not fully accurate due to the instability in the junction voltage, with small anomalies at 349 Kelvin and 350 Kelvin. These deviations introduce errors, slightly affecting the final outcomes. Lastly, the conclusion. Based on the data analysis from the graph of ln current versus voltage, we obtained the gradient M 26.7 plus minus 0.2 per V, the intercept C, negative 19.3 plus minus 0.2, the material constant N equals to 1.45 plus minus 0.01, and the reverse saturation current leakage, current I naught, is equals to 4.3 plus minus 0.8 times 10 to the power of negative 9 A. From the curved graph of voltage V versus temperature T, the gradient is M, negative 1.2 plus minus 0.2 MV per Kelvin, the intercept C 1.21 plus minus 0.06 V. The gradient of the graph is the temperature coefficient, thus the value of temperature coefficient is negative 1.5761 plus minus 0.0300 MV per Kelvin. And the energy band gap was obtained as VG0 deviation, which is 1.151 voltage. According to the whole analysis, we determined that germanium is the material used for the diode in the PN junction.